You know that phone in your pocket? Or the car you drive? Even the fork you ate breakfast with? Well, every single one of them started out as tiny little particles locked away inside solid rock. See, very few metals, like gold, are just found lying around in their pure form. The rest, they have to be literally torn from the earth using chemistry, intense heat, and a whole lot of energy. And that's the story we're going to dive into today. Okay, so here's our game plan. We're going to start with the biggest hurdle, why getting metal is so tough to begin with. Then we'll crack open the chemical rulebook that dictates, well, everything. We'll look at the big brute force industrial methods, fire and electricity. Then we'll check out how nature itself can be a miner, which is amazing. And we'll wrap it all up with what is probably the most powerful tool we have for a sustainable future.
So what's the big deal? Well, you can't just go out with a shovel and dig up a lump of pure iron. It just doesn't work that way. Most metals are chemically stuck to other elements, all bundled up in rocks we call ores. And the real kicker? The easy-to-get, high-quality ores? Yeah, we've pretty much used most of them up already.
Right. Think of it like this. Back in the day, we were mining high-grade ores, where a little bit of rock gave you a lot of metal. It was efficient, but those are getting super rare. So now, we're left dealing with low-grade ores, and that means we have to dig up and process these massive amounts of rock just to get a tiny little bit of metal. As you can imagine, that costs way more energy, way more money, and it creates a mountain of waste. And that leads directly to the environmental cost, which is not great. Traditional mining is not a gentle process, believe me. We're talking about carving enormous quarries out of the landscape, which completely destroys habitats. It also generates a ton of noise, dust, and traffic. And this huge environmental footprint is exactly why scientists are racing to find smarter, cleaner ways to get the metals we all depend on.
Okay, so how do we decide which method to use for which metal? It all comes down to chemistry. There's this sort of league table for metals called the reactivity series, and you gotta understand this. It is the absolute non-negotiable rulebook for metal extraction.
And the one player in this game that changes everything, it's carbon. You see it right there in the middle. Carbon is the great divider. If a metal is less reactive than carbon, like iron or copper, we can use that carbon to basically steal the metal away from its ore. But if a metal is more reactive than carbon, like aluminium, well, carbon just isn't strong enough for the job. And then way down at the bottom, you've got gold. It's so unreactive it doesn't even bother bonding with anything in the first place. Lucky gold.
So the chemical principle making all this happen is called a displacement reaction. The best way to think of it is like a dance-off. A more reactive, stronger element can just walk right up, tap the less reactive one on the shoulder, and take its place. It's a simple idea, but this one rule is the key to pretty much everything we're talking about.
All right, so we've got the rule book. Now, how do we actually apply it on a massive industrial scale? Let's look at two of the most important metals we use every single day. Iron, for all our steel, and aluminum, for everything from soda cans to airplanes. So here's the crucial contrast. Iron, remember, is less reactive than carbon, so we can basically win it with fire. We just cook its ore with carbon in a giant blast furnace. It's super hot, yeah, but it's a relatively cheap process. Aluminum, on the other hand, is more reactive than carbon, so fire just won't cut it. We have to bring out the big guns, a much more powerful and way more expensive tool, electricity. And this electrical process is called electrolysis. It's just pure brute force chemistry. The number one problem is that aluminum ore has a ridiculously high melting point, like over 2,000 degrees Celsius. To get around that, they use a really clever chemical trick. They dissolve it in something called molten cryolite, which totally slashes the melting point and saves a ton of energy. Then they blast the whole thing with a massive electric current to rip the aluminum free. But, and this is a big but, there's a costly catch. The process releases oxygen, which then reacts with the expensive carbon electrodes and literally burns them away. That means they have to be replaced constantly. Ouch. So given the huge energy costs and the environmental damage we talked about, scientists have started asking a really cool question. What if we could just get nature to do the hard work for us? And this has led to some absolutely amazing biological methods. Okay, this first method sounds like something straight out of science fiction. It's called phytoextraction, or sometimes phytomining. The idea is you grow these special plants called hyperaccumulators that literally suck metal ions out of the soil through their roots. They then concentrate those metals in their leaves and stems, so all you have to do is plant them, wait, harvest them, and then burn them.
You're left with an ash that's super rich in metal. It's an incredible clean process. The only real downside, it takes a very, very long time.
The other method uses even smaller helpers, bacteria. This is called bioleaching. There are certain types of bacteria that can essentially eat the rock around the metal. In the process, they produce this acidic solution that has all the metal ions dissolved in it. And this metal-rich liquid is called a leachate.
So now you have this liquid, this leachate, full of valuable copper. How do you get the copper out? Well, we go right back to our reactivity rulebook. We just add some cheap scrap iron to the mix. And because iron is more reactive than copper, it jumps in, kicks the copper out of the solution, and makes pure copper metal form. It is such a clever and really cost-effective way to finish the job.
All right, so we've seen how to dig metals out of the ground, and even how to grow them in a field. But what if the best source of metal isn't in the ground at all? What if it's already all around us, in our cities, our cans, our cars, and our buildings?
Okay, just look at these numbers. This is absolutely staggering. Recycling iron saves 70% of the energy compared to making it from scratch. That's huge. But for aluminum, it's an unbelievable 92% energy saving. Why is it so high? Because recycling lets us completely skip that crazy energy-guzzling electrolysis process we saw earlier. We just have to melt the old cans down. It's a no-brainer.
I mean, the advantages here are a total game changer. You save massive amounts of energy, you preserve the natural ores we have left in the ground, and you prevent all the environmental damage from new mining. But recycling isn't some magic bullet, right? It takes a huge logistical effort. You have to collect it all, transport it, and one of the biggest headaches is just figuring out how to efficiently separate one type of metal from another in a giant jumbled pile of scrap.
Let's actually think about that for a second. Let's say you're at a recycling plant and you have a giant mountain of mixed scrap metal, mostly steel and aluminum cans. How would you separate them quickly and efficiently on a huge scale?
The answer is so simple, it's beautiful. You just use a giant electromagnet. Iron and steel are magnetic. Aluminum is not. So you can just swing a massive magnet over the pile, lift all the iron and steel right out, and leave the aluminum behind. It's a perfect example of using a really basic physical property to solve a really complex industrial problem. And that really brings us to the big final question. Our entire modern world is built on these metals we extract from the earth. So, as we look to the future, with fewer high-grade ores to mine and an even greater need to protect our planet, we've got some serious choices to make. Will our future continue to be forged in fire and power? Or will we learn to grow it in a field with plants and bacteria? The answer, most likely, is all of the above. And remembering, of course, that the smartest mind we'll ever have is the one we've already built around us.